Hello and welcome everyone. So we have been discussing about exploratory data analysis, pre-processing of data, pre-processing, preparation, and this might also include feature engineering. We'll see that. Feature engineering. Okay, so just to remind you, the thinking that goes into this is like this. So you don't have to directly do EDA. So I wanted to. Usually people take EDA separately and then they take pre-processing and then preparation and feature engineering. So what I wanted to do actually is I'll take some data sets. We'll perform EDA because EDA is there for feature engineering, and you need to process data based on whatever you see in the data. That's why we'll be sort of intertwining them together. So we'll be doing EDA, sometimes we'll be doing pre-processing, but all of this goes into the data modules, because you have seen the pipeline. In pipeline, the data modules were quite big. We had data collection and data preparation, EDA, and all that stuff. Because as I told you, more than 60% or 70% of time you will be working with the data, and you will have to clean data, and you'll have to understand data. So that's why we'll take this in that way. We won't be separating the modules. We won't be saying I'm just doing EDA. So all these things will be intertwined into each other. So in this, we're in the topic of handling missing values. Handling missing values. This is what we were discussing. So in that, we saw different types of missingness that can arise because of data collection, or the process itself. Maybe when you're doing something and data might get corrupted and howsoever, and we saw different type techniques. And then we saw, okay, if we now want to handle these missing values, okay, so what are different types? So we said the first type is univariate. So by uni, you mean you just use that one variable, or maybe some other one variable you can use to impute this missing value. So one was you just drop that thing and then you go ahead. But because the problem is in the approach, you lose a lot of data, and maybe sometimes it's not convenient for the data sets where the data collection is quite costly process. Sometimes when you just collect one point of data, it becomes it takes, let's suppose, if not thousands, some hundreds of dollars to collect the data, and at that time it's not an option. I'll say dropping the data is not the option for in real time. It is not the option in 90% of the cases, or even more than 90% of the cases. But sometimes you have a lot of data that you can afford to drop the values. That's why we came up with the imputations. We said, okay, now if we cannot afford to drop the data, if we cannot afford to delete the rows or columns where there are not a number value or missing values, so what should we do? We should somehow handle these missing values. We should somehow impute these values. We should put some artificial values so that our algorithm performs better. So what a machine learning model that we use, because it learns on the data, and the goal of the machine learning model is to generalize. It's not to memorize. You should not memorize the data, not to generalize. So in order to generalize, you should give it a good distribution. The distribution should be quite well. So whatever data you have, it should represent the distribution. So when you have missing values, that means you have incomplete information, and that implies that you should handle that. The first thing that we saw in there was univariate imputations, in which we just use one variable, and based on that we impute the values. So I think in that we saw mean, mode, imputation by mean, imputation by mode. I think we also saw imputation by median. We also saw imputation by arbitrary values. Okay. Was this it, or have we discussed something else? So while we're discussing all these imputations, we said you have to analyze data for different things. Before imputation, what was the distribution of data, what was the variance, mean, and stuff like that. All those values which are necessary for data, which are called as statistical values. So all these things that you have to see. You have to see if the variance was changed. You have to see if the mean got shifted. You have to see was there correlation shift or something like that. All of these things should be done. So whenever you are doing these imputations, you should not mess up with data. So somehow this data should still be the representative. You should, whatever distribution you have, or you have incomplete information, your point of handling these missing values is to somehow complete that distribution. Okay, that should be the goal. So that's why I said whenever you're imputing the values, so if you are imputing it by some value, by mean, median, mode, you should have a rationale behind that. The reason for that was because you have to make this you have to reason about it. Okay, if I impute it with this value, so what is the rationale behind that? And it should be interpretable. That's why we said if you, let's suppose, have some arbitrary values, the arbitrary values should be from the domain. Okay, so when you impute, so you should do these tests before and after. So you should see all these things before and what happened after, because we saw that on different techniques. When we change these missing values by mean, we saw, okay, what happened to the distribution of this feature, and what happened to, suppose, variance, what happened to mean, median, mode overall, and all these things should be done. Okay, and this is not where you should stop. These are just the things that we can do if this is numerical, but you guys will be working in different domains, and the data set might be entirely different. So you will have to even come up with these things. Okay, so something like that right here. So I can come with distribution. So there are numerical values, are categorical variables. So I can say, okay, this is the distribution which was there, and with the missing values, I can complete this distribution. But let's suppose now your data is entirely from different domains. So your thinking should be, can I come up with some thing of my own? Can I come up with some quantification or some methods by which I can see what are the impact? So the principle here is, I'm not just checking the variance, the distribution, and all these things. The principle is how the data, I am basically seeing the change. That's the principle. Okay, you have to somehow track this change. Should not change the distribution so much. Not the distribution, should not change the data so much. So I'm using distribution because that's what usually happens when we have numerical and categorical data. But I'm rather trying to inculcate a different thinking in you people. That is, if you have any different data set, it's not necessary that you'll just check distribution, variance, and all this stuff. But what you should do is, the principle is, you should see change, how the data set got changed, and now you'll have to define it for yourself. You'll have to see, okay, what are the mathematical notions, or what are the quantifying criteria that I'll use to measure this change. So here I'm measuring the change. So distribution, I'm plotting the distribution before and plotting the distribution after. The point there is, I'm seeing what's the shift in distribution. Okay, so this is the thinking that you should have. It's not that you just checked, okay, distribution remained the similar. But let's say you have the data where the distribution made no sense. Okay, the change should have been tracked by some other means. This is your guiding principle. Okay, the guiding principle is, whenever you change something, whenever you impute a value or do something in that data set, so you should track this change. Have I changed something? So you can use distribution, you can use statistical measures, you can use some other things. That depends on you then. Now we stopped our univariate analysis on this arbitrary values, and I told you that we'll have a I'll ask you guys, okay, what are the different things that we can do again. So okay, and today I'll start with maybe Fahad. I think mean, median, mode, and arbitrary values were the things that were discussed by Asif and me. And now, Fahad, do you think anything else can be done in univariate analysis? In univariate, you have data like this, and you have some values which are not a number value. Let's suppose this value. So except from mean, median, mode, and these arbitrary values, do you think there should be some other method, or what comes to your mind when you think, okay, I can impute? Consider this as numerical values. Consider the columns are numerical right now. So this is F1, F2, F3, F4, and F5. Okay.
I actually have an idea, but I don't think it would be univariate.
Yeah, I'm right now focusing on univariate. We can go ahead with the multivariate maybe after that. So do you have any ideas for univariate except for this mean, median, and mode, and these arbitrary values? What do you think can be done? Do you have any ideas, or any other person who has any ideas? How can we impute this number value? Let's now see these things जो हमने डिस्कस की, एंड विल सी कि लोग कहाँ कहाँ पे है. बट आई वाज क्वाइट हैप्पी कि हम लोग इस पे खुद आए. सो माय पर्पस इज समहाउ सर्व्ड कि जो मैंने बताया था, विल लर्न फ्रॉम अ रीडिस्कवरी पॉइंट ऑफ व्यू. Okay, now let's see it one by one. The first thing that we discussed was that you change it with the interquartile range. So technically that has been named of end of distribution. What is this end of distribution? Can you please mute yourself if somebody is not on mute? So this is a method where you fill these missing values with some extreme values, usually at the tails of, like, let's suppose you have this 99th percentile. That's why it's called end of distribution, because you want to give it a sense so that these values somehow have some significance. This represents some unusual category. So you just represent some extreme values. That's why it's called end of distribution. You can have, let's suppose, you'll see it. You can see these points in outliers or something like that. Okay. So this end of distribution method basically, it can this approach can help in some where you think that missing values themselves have some significance. Let's suppose they represent some unusual category. Okay, the rational part that I'm explaining now. So why do we do that? So we do that in the hope that we think these points, let's suppose either they're outliers, that's why we make them outliers, because if you see this 99th percentile, they usually are outliers because they don't they're not at the mean value, or they're not on the median mode value. So we want them to give some extreme value so that they look unusual, okay, or maybe outliers, or you make them unique, you somehow make them unique. So the rationale behind this is these things. And so what do we want to achieve with this? So that whenever any model, it can be a deep learning model or a machine learning model, it somehow we give it a sense, we give it more information about this. So we give it more information that this value, when we replace it with this value, so somehow it should pick up that these are the unusual categories and they had missing values, so that when it learned the distribution, it somehow has a sense that this information is still there, and we did not just make data out of random. We just took a percentile and put it there and conveyed to the model, okay, these were some unusual categories, okay, or something, and this is what we want to achieve. Okay, so when should we use this? So when missing values may represent anomalies or outliers, that's what we said, what I said. So to maintain the distinction between the input and the observed value, okay, and there is a distinction. This is when you should use these values, and usually it's used for skewed distribution, where imputing the mean and median might misrepresent the feature. So what is the meaning of skewed distribution? So usually you can have a symmetrical distribution like Gaussian distribution, but if you have a skewed distribution like this, something like this, where there is a huge skew, left skew, right skew, and you can measure that by kurtosses and things like that. So here in such distribution, so what you do is, so in order to not mess up with the distribution, not mess up with the skewness, and you might feel if I just imputed the mean, median, or mode, so it might misrepresent the feature. So it is better to just represent at the end of distribution. Okay, and now I'll go to again both the methods. We'll see how to do it in pandas and how to do it in scikit-learn, and then what we'll do is we'll see that we'll basically track the change. Okay, how to track the change, because now I'm working with numerical data. I can use distributions, I can use statistical features like variance, mean, mode, and how they got shifted, and something else. Again, to reiterate, whenever you are working with data set, the guiding principle is you are tracking the change. You want to see how I changed something. So accordingly, you will have to come up with the quantifying metric. You'll have to come up with a metric which will somehow quantify this change, which will somehow define this change, and you can track that. Okay, let me come up with the code window. Okay, this is the code window, and here the first thing is, we're working in a data set where we had this glucose, blood pressure, and all these things, and I think it was diabetes or something. We're saying that the patient is diabetic or not. Okay, now I'll just copy paste a snippet of code and I'll explain you what that is. So if you see over here, so I'm saying df end of pandas. I'm just creating the copy of the original data set. Okay, then I'm saying extreme values. So you can see our glucose, df glucose, and take this quantile, that is 99th percent quantile. I'm just taking the extreme value of the distribution. Okay, similarly, I'm taking the first percentile. Okay, this was 99th percentile, and this is a first percentile, again the 99th percentile. It depends whatever value you want to choose. Okay, you are just taking one value, and these values are sort of extreme. Okay, if you see, this is end of the distribution, and this end is basically the tail portion, and this is the head portion. Okay, and then I'm again applying this value for the column. I'm taking these three columns: glucose, diastolic blood pressure, and BMI, and then I'm just filling these. If you see, I'm running a for loop, columns value, and taking these extreme values to items. So item, because this is the dictionary, so this is the items in that. And after I have items, so I am filling this value, df and items, and selecting that column and filling the value by this value. So value, what is the value? So where am I getting this value from? So this value, basically I'm getting these from, because items, they'll give me these keys, and these are my values. Okay, because it's the dictionary. So I'll get this column and values. The extreme value to items basically will have two values. So one will be glucose, that is column value, and this df glucose dot this quantile, this will be a numerical value. It will be given to this value. Okay, that's what I'm filling it. I'm selecting that particular column and filling that with particular value. And this is where I'm at the end checking it if there is still some not a number value. Okay, so if you see, if I just run this, oh my god, I have to run this again. I have to run all cells. Okay, let it run. Hopefully there is no error. Okay, so you can see now, I think this ran gracefully. So this is what I got. So end of distribution, imputation completed. So did I got this somewhere? This is showing me some warnings, but you can just, because I'm just making change in the portion of data set. That's why it is showing these warnings properly. but I hope this got changed. So if I just where am I changing this? Df end of column. So I'm changing it in place. Okay, so if I just see this, okay, yes, it is getting changed. So if you see this, so it's showing end of distribution, imputation of pandas completed. Okay, so this is the code snippet for that when you do it in pandas. So you can do the similar thing in scikit-learn. Okay, the scikit-learn's code is somewhat similar, but the only additional thing is you will have to make objects before using that particular class, because there's a class simple imputer which we are using. So from scikit-learn we're using the simple imputer class. The first thing, again, creating a copy of the data set, and again I am creating these list of these values, df glucose, and then giving the values. Okay, and then for other I'm just keeping none. Okay, and then I'm again doing the same thing for I, and this enumerate this df columns, and then I'm saying if extreme value of list I is not none, if it is not none, then only change. Okay, so because I just want to change the values for these things. Okay, for this glucose, for diastolic BP, and for BMI. That's why I'm checking this condition. If extreme values are not in this, so if that is none, then you should not do anything. If it is having certain value, then change it. Okay, then fill value is this value. So I'm making it an integer. Okay, if df column of dtype is this, else give this value. Okay, and the strategy is again constant, and then fill value is the fill value. Okay, and this is what we have seen, I think, in a previous session also we were doing this, but here just doing this additional check because I'm making a list out of this. So just if I just do this, so again you can see that, and the distribution imputation scikit-learn got completed, and then you are seeing these values. Now what you can do is you can again plot the same plots, which we don't want to plot now. You should be by now experts in plotting and checking tracking the change in the distribution. So this was the first method which I think Fahad mentioned. So he just mentioned one thing. He said we can maybe have 75th quartile by which we can, or maybe interquartile range, that number can be used to handle these missing values. So this was the first approach that we had in our discussion, interquartile range. Okay, so what are the other methods? The other methods that we discussed is time series. I think we'll take it separately, and maybe prediction also will take separate. I'll go in order. So in the order I have written them, I'll take in order. But do remind me if I just miss something. So this was when you do this imputation with the help of let's suppose you take these interquartile range, or maybe 99th percentile, or end of distribution, howsoever you like it. Okay, and I gave you the rationale behind that also. Now the other thing that you can do is call as the random imputation, which surprisingly nobody told me and we didn't discuss it. So what is this random imputation? Okay, you were pretty close to coming up with this. So let's suppose now you have this data. If you have the data like this, okay, and we have not a number value over here, and then there are values. Okay, let's make more values, something like this. If there are values, so now what we can do is, if we have this nan value over here, if we want to replace it, so can we think this f feature? So this is f1, this is f2, f3, f4, f5, f6, and f7. Think this is a distribution. Just pick up these values randomly from the other values which are not a number value, so which are not number value, which are basically not missing values, not null values. So what we can do is we can just randomly sample from it. So you can randomly sample from this. That's why it's called a random imputation. It's not like you just take a number. So that was arbitrary imputation, while we just take a number which probably have the rational in the domains. Why are we choosing that number? But here the random imputation means you're taking this number at random. So but where do we get this number from? You're taking this from these features. So this, let's suppose this feature 2, it will follow some distribution. This feature 2, let's suppose, follows some distribution like this. Okay, and this distribution is the all where we have not null values. These values are not missing values. So now what you do is you randomly sample values from this. So let's suppose these are the values, you randomly sample some value, something like this. Okay, this is again giving me hard time flipping this. If you see this, so here when you are replacing this nan value, so you are sampling randomly from this. Okay, so this is the random imputation. So random imputation in simple terms is a technique used to fill these missing values by replacing them with a random value, but that is sampled from the observed distribution, okay, of the corresponding feature. So this is sort of a deterministic, like these deterministic methods, like we have this mean, median, and mode. So this has some randomness associated. Okay, so it introduces this variability in data. So it can be beneficial so that you can preserve the original distribution of the data. Why? Because you have to sample it from the original thing. So if let's suppose some number, let's say if this is a distribution and some 10 number, it occurred most of the time. So there is a high probability that you will sample this number 10. Okay, so if this number 5 is in the extreme value, let's say this is 50 value, so there is very low probability that you will sample this number. So somehow it can preserve this distribution. Okay, is this one clear? I think we did not discuss in our discussion when we were discussing this. This approach is also used.
Uh,
Yes. The question asked was if we randomly select any number from it, so what's the significance of that? So I said it depends on sampling. So I'll tell you like this. So what is the meaning of sampling basically? So if we have a box like this, in this box we will have a couple of balls here. We have red balls and we have, let's say, these purple balls, and let's say we have these orange balls. Orange ball is there. Okay, now this is data. Okay, we have this red, we have purple, and we have this orange ball. Okay, this is our data. So now if you plot this, so if you plot, let's say here you have frequency, okay, here and here you have color. So red has, let's suppose, color 3, so you can say 1, 2 and 3. So this is red and this is color 3. Again purple, this is purple, let's suppose color purple, and it has 2 balls. This is the distribution, and this is the 1, and this is our orange ball. So somehow if you plot this distribution, oops, I'll use red, respecting the color, which I usually don't. Today I feel like an artist, I will respect the colors. So here some sort of distribution is there. So now once you sample it randomly, why am I saying random? You shuffle it very well. So you shuffle this box very well. So you don't have bias anyway. So when you will just pick up a ball from here, so there is a high probability that you will get a red ball. So how much exactly? So if these are 3 balls and the total ball count is 6, 3 by 6, there is half chance that you will have the red ball. That's what I mean by sampling. Okay, when you have these values, so there will be values which will be frequently occurring. Okay, and it'll have particular distribution. So when you sample it according to distribution, and you actually randomly sample it, so but it will represent the distribution. Whenever you are sampling it according to the distribution. It's not that you are yourself introducing some randomness. No, but you are just shuffling with the data. You are shuffling the data somehow, so you don't bias. You don't just, let's say, only focus on this orange ball. You don't do it, but you shuffle the ball very well, and then just take your hand and put it in the box and take it out, and then there is a high probability that you will get this. So whenever you sample it, you will see that you are respecting the distribution. So that's where this random word came from. So you're basically randomly sampling. It's not that you are just putting a random value. You're randomly sampling out of the distribution which this feature has. Is that clear? Okay, just to reiterate, so this is a bit better than the other techniques because there they may change distribution. So here the advantage is that there is a high chance that this sort of strategy will not by this randomness, it will preserve the distribution. Let me just finish this. This will preserve the distribution. So because of random sampling. Okay, this is not a random value. Okay, people might get confused that this is just a random value. It is not a random value. It is random sampling. So you sample it, you shuffle it very well, and this randomly take out a value. And by randomness, we try to respect the distribution. We try to see that okay, this distribution should be respected. Yes, you have a question. Go ahead. So the first thing that I said is when you do this random sampling, please keep this in view that you are not randomly just picking any number. No. You are shuffling it by random, you are shuffling it, you don't introduce any bias, and then you are selecting that number. It is like what I mean by random is that we just maybe spend some 2-3 minutes to define this random. What do I call random? So let's suppose if I have 2 choices only, I have, let's say, I have to sample value 2 and value 4, and now what I want to do is I want to sample them randomly. So what I mean by sampling is, so I'll say I'll flip a coin. I'll flip a coin. So if it lands on heads, this I'll sample 2. If it lands on tails, I'll sample 4. Okay, now I think if this coin is fair coin, it's not biased coin. So you know that there is a 0.5 chance it will be head, and there's a 0.5 chance it is tail. So that's why I mean when I sample this, there's an equal chance. Okay, and we have only, and if this distribution is uniform. Okay, if this distribution is uniform. So I am not biasing my value. So you have this 2. Let's suppose you have 100 values which have this value 2. And you have 100 which have this value 4. Now when you shuffle it together and you randomly sample, I mean that you are not skewing the distribution. And here I just associate with a coin because coin is a fair coin. I just I flipped it, and 0.5% chance is head and 0.5 is tail, because this is uniform. But now if you have this distribution, the distribution is like this. If your distribution, it looks somewhat like this, which is not uniform at all, it may be Gaussian, it may be some other distribution which has no name. Now in that, the random thing is, I'll shuffle all the numbers, I'll not bias towards any one number. Okay, the high probability is that when I sample enough number of times, okay, that's frequentist approach of probability. Okay, if you just sample yourself 50 times, you'll probably get a distribution like this, you'll get a proper distribution like this, say you got a skew. But the more times you do it, the more times you keep on sampling, so you will get something like this, you will get something similar distribution. That's what sampling means. That's a frequentist approach to probability. If I say that probability of head is 0.5, but I'm saying that, okay, can you just toss it twice, so both the time maybe tail will appear. So then it means, does it mean that the tail has one probability? It does not mean this, because we have less number of experiments. So the more number of experiments you do, you basically go close to the distribution. Okay, I could have shown you that by simulation, but I'll leave that thing, the probability part. So here, what I mean by this random sampling is, so I'm basically shuffling it, I'm not biasing towards anything, I'm not just picking up certain values. I'm saying, okay, I'll randomly shuffle the data, and whatever I'll pick, I'll pick it based on the probability, based on the distribution, and I'll rest for the distribution. And because of this, the distribution gets preserved. Okay, and then it avoids bias, which I discussed in the sampling. So by that I mean, unlike this median and mode imputations, it does not create these artificial clusters or some identical values. So it reduces the risk of bias, because when you impute the values with mean or mode, so there will be a lot of values, n values in some features, which will have this mean value, and then they will form a cluster. So when they form the cluster, so it creates a bias in there. Okay, let's suppose I have this value. So let's suppose there were some 500 n values. So all these 500 values, if I replace just with one number, say mean, mode, or median, so what will happen is they'll create a cluster. They'll create some cluster of that, and there will be a lot of same occurring values, and that will introduce the bias. So here you know that these numbers won't get replaced by just one number. So they'll get replaced based on the what we sampled. Okay, when we shuffled it and we took a number randomly out. That's why we call it randomly. It is actually not random key. We just took any number, we wrote 23 and we just dropped it. By random I mean I shuffled it very well and then pick it up. Okay, by that I mean random sampling. And then we got different values over there, and it avoided the bias. And it's a straightforward approach. Okay, and this is the most important thing in here. Okay, but the problem again is it relies on the randomness. The results can vary in each run, which I told you, because the frequentist approach. And now whenever you sample, let's suppose you did it once, so the result will be something. So if you again repeat the same thing, so the result can be different. Okay, that is the problems with that. So it relies on randomness. So as Muzaffar already rightly pointed out, it's a game of chance. Then sometimes a number might be sampled, sometimes it might not be sampled. So with each run, the things can be changed. Okay. And again, it can the outliers in the observed data may also be sampled. If there are outliers, they may be sometimes also sampled. If you just, let's suppose, have 2, 3 n values, so then this sampling is not good. Okay, the problem in that is because it will just, let's suppose, if you sampled one and it was an outlier, so it will again create some sort of like disturbance in the data. Okay, and we have a question. I think I couldn't read it. The question is, can somebody read the question for me, please? I couldn't see it on the screen.
The question is, for shuffling, do we have any methods?
Yeah, we can introduce. I think I'll leave this topic to probability because usually people don't touch that. All these things come in probability. How do we shuffle? So shuffle by definition means randomness. You shuffle it random. By shuffle is a little word in English which means you randomize the thing. That's called shuffling. Okay, and but we can introduce bias also. We can introduce bias, and that's what these magicians do. Okay, when they just shuffle it in a certain way, and it looks random to you, but actually he's not shuffling it random. He's not shuffling it at all, because by shuffling I mean it should be random. And we will take it all these questions in probability. Okay, that's how important the probability is. And now if we have to do this, okay, so how to do that? We can do it again with pandas, and we can also do it in scikit-learn. So I think scikit-learn, but does it have? I don't know if scikit-learn have that. I have implemented this with the help of, I think, NumPy and pandas over here. So let me just go to the code window. Concept is more important. The code is not that important, because you can find code anywhere, and the thinking is important. That's why I don't stress much on code. Many people you will see writing the code, but I think you can find this code anywhere if you just maybe type it on GPT or something else, or maybe you can just go to some books, you will find code snippets. But the more important thing that you have to go through is understanding part. You have to understand and build this thinking. Okay, how do I think these things? Okay, now if you see this is the random imputation function. Okay, it replaces the values in the column with some random samples. Okay, so here I am choosing this np.choices. Okay, this is observed values. So we'll use this a lot. This function will use a lot in neural network. So now let me explain you the function, what it does. The first thing is I am creating a copy data set, a normal thing. So now if you see this function, what it does, so it will take observed value and it will take this. So this is the observed values. Okay, and I will take missing indices. So these are the missing indices. So all these indices where the values are missing there. So what will it do is it will say imputed value, which value what it will do is it will say np.random choice. It will take a value from these observed values. Okay, and that's why I made this. These are the original non-missing values. I am taking a value from non-missing values, but this np.choice, it respects that. It respects the distribution. So whenever you use this, so it respects that. So again, it's saying size is this of some and replace is true, and and you should replace that value in place. So again, and then I'm saying df dot location of this missing value indices, change it with this. Okay, so here if you see now, if you see this code, so this is going to the column and df dot impute dot columns. And this is that column which this is that data frame which we created because from the df copy. So if df random compute column is null and dot sum is 0, so only for the column which has missing value base, that's what it's doing. And then for these things, what we are doing, we are calling this function. So again, to reiterate this function, what it is doing, so initially it is coming up with all the non-missing values because that's where we have to sample it from. Then it is coming up with the indices where there are missing values, and then it is taking a value. This is randomly choosing the value from these observed values. Okay, and then it is replacing that missing indices with that value. Okay, this is what it is doing. If you see it over here, that's what it is doing. And if you just run this cell, and this is doing data random imputation complete. And this is what we did. We just implement this function from scratch. I hope there will be some function from the pandas, or maybe I don't think this can be done in scikit-learn, because otherwise I would have written it. This notebook has been made, I think, quite some time early. Okay, but if you can do it, this is the implementation. I think this is pretty clear. And now we can also calculate the stats, how they got changed. So this is before and after. Mean was this. You can see that how well it respects the distribution. 3.8, 1 to 1.68, and 70 somehow, and then 72.54, 72.50, and there is a slight change. But some of the distribution will remain similar. If you just plot these things, these are the graphs for all these features. This is comparison of mean, before, and random for all these values, glucose and diastole, and this is the graphical representation of what we saw over here. And I can also show you the distribution actually, which I was constantly telling you. Okay, but I hope that you understood it beforehand. So let me just spend some time over here. So if you see this, so this value is the value of glucose. Okay, so you see glucose is a particular distribution. You see glucose has this distribution. So whenever you sample, there is this much probability. Like if you treat these as the probabilities, okay, if you think this as PDF, if you think this as probability distribution function, okay, which we have discussed a bit, not too much detail, but you understand that this can be thought as a probability distribution function. That is, this 100 and this point has high probability of being there. So when you sample from it, so this number will occur frequently or has more probability of being sampled if you just take it randomly sampled. You are not biasing the distribution. You can see this is the distribution. Okay, and if you see before and after distribution, it quite looks similar. If you see both of these distributions for glucose, it looks similar. Okay, and if you see overlay distribution, so there is a slight change over here, but it somehow looks more or less similar. And this is for the glucose only. So this was before and this was after distribution, and this was the overlapped one. So you can check with all the features here. You just need to change this one. So here I have taken glucose. You can take some other values also, and you can get these three plots. You'll get the before plot and you'll get the after plot, and you can overlap them together. And you will see there is very slight change, not much change, and it somehow respects the distribution. Any questions on this? Okay, now let's come to this missing indicator. Missing indicator. Okay, this is missing indicator imputation. So as I said, this missing indicator imputation is a technique. This is used to handle missing values by data augmentation. What is the meaning of augmentation? You augment data, you append some more data into data set but with these new binary columns. Okay, these are called as indicator columns. That record, it says whether the value to the corresponding column is missing or not. Okay, that's the approach. Okay, this approach doesn't directly, basically it does not impute, it actually does not impute, but tells the algorithm. Okay, so this tells the algorithm. So what does it preserve? So it preserves the meaning, it preserves the meaningness of missing values, the meaning of missingness. Let's have a bit of discussion on this. So again, I'll just reiterate how it works. So this is our data. Okay, and these are features, let's say. So feature 1, feature 2, feature 3, and so on. And then we have these not a null value over here, then we have not a null value over here. So what we basically do here is we augment the data. Okay, we augment this data with some more data. So we have some more columns. So this will be an indicator. I'll call F1 indicator. I'll say F1I. Okay, then similarly F2I and things like that. Now, as Fahad said earlier, this is some sort of mask. Okay, where you have this not number value, you'll put 1, you'll put an indicator, and rest you can put zeros. Okay, or we can call it not just 100 encoding, some sort of encoding. This is the encoding where you encode this thing where there are missing values. Okay, so what I said is it preserves the meaning of missingness. Sometimes it's very important to see. Sometimes the missingness, the value is missing, say, it might convey some information. It's not always the case that if you have a missing value, it's incomplete information. Sometimes the missing itself carries information. This might say something about data. This might say that this missing value is there. It might have a reason. Okay, and it might have a pattern of some sort. And if you impute the value, you somehow take that information away, because you want machine learning or deep learning models to learn as much as possible. Okay, now if you are in a domain where you think that this missingness has some sort of value, it has some sort of meaning with it. The meaning could be, let's suppose you can find correlation. These higher income, the individuals who have, you want to find a rich individual. If you see that a guy has not reported the income, it has a high probability that the guy might be rich. And if there is that sort of meaning associated with this missingness of the values, so if you want to preserve that, if you want to tell your algorithm, okay, somehow this is how you should capture it. So that's why you append it, and this is the rationale we think. And how algorithm does it, we might have no maybe means of knowing that. But as I said, that this was used in a competition and it performed really good by just augmenting this more data. And we hypothesized that maybe this thing, when you have these indicators, so what you do is you give additional information to your algorithm, because in that case scenario, maybe this missingness might have some value, might have some meaning associated with it, and you're giving the algorithm additional information that there are missing values. You probably are not imputing them, and you're just putting the indicators over there. I think you have a question. Yes, go ahead. So now we saw that you can just append this more data, and the thing that I told you about this is you are somehow giving an additional information. Okay, this is giving me a hard time again. Okay, so it preserves the miscellaneous information. That means in some data sets, like medical data sets, a missing test result could indicate that the test was skipped. It was not at all done. Okay, that now the missing value it contains some information. Okay, if there is a missing value, then it says that the test was not done, and maybe patient was hiding something or something like. And there are cases like that in medical. And as I said also, in the other case, if there are individuals who have a very high net worth, they don't usually report their income. Okay, maybe because of taxation or something like that. So this missingness itself has some meaning. So in that case scenario, what you can do is you can augment the original data set by just appending these missing indicators. Okay, and it has been seen that it performs really nice. Okay, and then you can again what you can do is you can implement it from scratch, or you can use the scikit-learns package, and then we have the missing indicator is there. So you have a separate class missing indicator. I'll just show the code. So if you see this, again creating a df copy, this is the simple imputer, and where I'm just using mean, which was the case, that's what Mahmoud asked. If you have these NaN values, what should we replace them? So you can choose a simple number or a mean. Maybe I just use simple imputer for these missing values, and then I'm appending the data. Okay, this is the missing indicator. Okay. And sometimes what you get, if you have an algorithm which works in NaN, so you don't need this line also. So but here we have used strategy mean, so you can test it with median also. You can choose other things also, what value should be replaced, but appending this data. Okay, now what you are doing is you are giving algorithm additional information if the missingness carries some information. So again, then you are saying this missing indicator, doing this, and then you are imputing this. You are saying x impute is equal fit dot transform this, and then x indicator is fit dot transform this x, and then you are combining these things together. Okay, so initially this is the first thing where you have this imputer. So this is imputing these NaN values, and this is putting the indicator, and then you are clubbing these data together, and this is the combined data now. Okay, this is the combined data where you have these indicators. These are the indicators. You see mostly zeros because there are very less missing values, but if you just fully expand it, you can see the full data set. Okay, and then you can see, you can maybe perform an algorithm on this, and probably whatever you want to do. Okay, I hope this is clear. Any questions on this? And this was very unique. When people did it, I think they won a competition based on this. So this is what I want to inculcate in you people. And there might not be a technique in the literature, but you can find, okay, let's suppose in medical data case, they found, let's say, this missingness has some sort of meaning associated with. Can we do something which is not conventional, which is not written in the books? Can we think something? Can we have a discussion and come up with some technique so I can handle these missing in a better way? Okay, and that's what they came up with. And I want you to think in these directions. When you see data set, go with the open mind. Don't think that you don't have capability. Don't think that you probably don't know this, because you have enough knowledge about this, and you just need to put it together, and then maybe you can come up with a new technique. And that's what science should be. That's how science should be treated. You should not always rely on whatever is there in the literature. If you always rely on that, then the first thing, you are not doing anything original. Okay, and that's why you should come up with the open brain, and maybe if there are techniques, use them. If your problem is so novel that it needs some new methods need to develop, and you should be open to that also. I have seen many people who just look on the internet, and that's what I'll just pause the recording over here. Okay, now we have seen these techniques. Missing an indicator, we have seen this, and we can also do linear combination. Okay, that linear combination. I think what is this linear combination? Because we are in the univariate analysis. So what you can do, you have a feature F1. I think this again, you won't find this, and you won't find this maybe on the online. But here, Muzaffar is the one who came up with this, and now we can give it a structure. So you have these features. You have, let's suppose, this NaN. Okay, and if there is a temporal aspect to it, if there is a temporal aspect, so what we can do is, so we can associate a number over here. Okay, let's suppose, take all these numbers which came before this NaN. So you can take a combination of these. So usually, let's suppose the numbers which are closer over here, you can give them higher weight. So usually, let's suppose you give the weight of, let's suppose, from here you give weight 1.5. So, and you slowly decrease it, or maybe you keep for last three values you give them higher weight, and for all the other values which came before to it. So what you can give them constant weight, and you can come up with the number. Let's suppose before you have a number like this, you have 2, 4, 5, 8, and then you had not a number value. And now what you want to do is, you want to come up with a number over here. So you can take a combination, you can somehow combine these numbers for this number. So, but why should we do it? The rationale behind this can be, okay, let me just remove this code window. The rationale behind this is that when you have this 2, 4, 5, 8, and you believe that somehow this future number is getting impacted by the past number. Okay, if this was an NaN number. So I'll give an example. Let's suppose you are working in a stock market. There you know that the previous prices somehow has an effect on the future prices. Okay, so if you have the data like this, where you have this NaN values, and you believe that the previous numbers, the numbers which came previous, have somehow some effect on what is next. Okay, so what you can do is, you can combine these numbers in a certain way. Okay, which we'll call the linear combination approach. So, but what I'm saying is, one additional thing you can do is, you can give more weights to these things. You can give more weights to which came consecutively, which came just before it. As I said, you can give weight 1.5 to this, 1.5 to this, and 1 and 1 to this, and you can just combine them and then divide by the number of observations like this. You can say, let's say 2 and then plus, maybe add, multiply, howsoever you want to take the combination. Okay, and you can take 1 by 4, and you can take 1.5 multiplied by 5, and you can take 1.5 multiplied by 8. Okay, and then maybe you can divide it with 1, 2, 3, 4 observations, something like this, and you can come with the number, and you can just fill it with this. Okay, so what's the rationale? I said, if you believe that this number is somehow impacted by the previous number, and this also covers our time series, because in time series also you do this thing a lot. So you replace with just the previous number. Okay, or you can just maybe roll the window, you can take the mean, you can take some other values of some past values, things like that. Okay, and this approach also makes sense, that we discussed. I have not written the code for this, because this is the approach that we discussed in the discussion, and you can write the code, for it, not difficult one. Okay, is there anything else that we left? I don't think so. Is there anything else in the univariate analysis? Indicator, we covered it, and this 0 1, you can just put a number there, and this linear combination, and this time series also, which we cover. And one is prediction based. Okay, we will take this also univariate based. Okay, so I'll tell you how to think about this prediction numbers also. So okay, prediction based approach, but this is in the univariate. We'll take multivariate, and there we'll do proper predictions. So now it's, if you have this feature f1, you have feature f1, you have these values over here, and then you have NaN values. Okay, so now again the assumption here could be, so if you are making a prediction, you are saying that I'll make prediction based on the previous numbers, and again assumption could be that somehow your previous numbers impact the future number, as in the stock market. Whatever was the price yesterday will impact what will be the price tomorrow, or somehow like that. So what you can do is you can use a model over here. Okay, on all these features you can use a model. Okay, and that will predict this future number, that will predict this future. So you can think it as a time series data, while you have data like this, and in between there is a jump over here. Okay, so what you can think is, you can think that I have data available to me is only this much. Okay, and now you can make it as a prediction algorithm. You can think, okay, I'll use an algorithm which will take this data and predict for the next. Okay, and there are a lot of methods. There are methods like I'll say, like in statistical methods there are moving averages. Okay, and then there are whole books written on these things. Okay, moving average is one method by which you can see what things are there. There are methods like ARIMA, okay, and the autoregressive, I think, intermediate moving average, and there is methods GARIMA and SARIMA, and all these methods. There's a method GARCH. Okay, this is basically for the next prediction. Okay, if you have this previous data, what will come next? Okay, these are all statistical methods. This you will learn if you work with time series data. When you work with time series, you will learn all these statistical methods. So here, if you want to make a prediction, so if you believe that somehow this value is impacted by the previous value, so you can use these previous values to come up with the next value. Okay, this, and you can use a good algorithm, or as I said, you can use moving average value, you can use advanced, these are all moving average values though. Okay, but if you believe there is seasonality, there is trend, and you can use all these methods which I just mentioned over here. Okay, and these things can be taken as input, and this can be thought as next prediction. Okay, and this is what can be done in univariate prediction. Okay, any other questions you have on this? Okay, we'll close our session here. So I think we have covered a lot of methods that are univariate in nature, and we have covered almost all the methods that are mentioned in the literature. And I'm not 100% confident that I know all the literature, but this is what I have written this notebook, I think, way back, and these are the methods that I encountered that time. And we have discussed some other methods also, which were the output of the discussion that we had together. And if you have any questions on these, please feel free to ask. Otherwise, I'll stop the recording over here.